Hi all, welcome to our talk today on HebNet, a simplified Hebbian learning framework to do biologically plausible learning. My name is Manas and I work at the Institute for Infocom Research in Singapore. This paper has been accepted to NeurIPS 2020 Beyond Backprop workshop. So firstly, what is Hebbian learning? So Hebbian learning is an algorithm for training neural networks which is biologically plausible because it does not require any error or feedback to be backpropagated. So if you look at how a standard backprop network works, we firstly do a forward pass at the end of which we calculate an error, and then this error is backpropagated through both the layers. In HebNet, we do one step slightly different. We still do the forward pass and calculate an error which we backpropagate over the last layer, which we use as a classification layer. But then the layer before that, which is the layer that we actually use to learn the representations, is the Hebbian layer where we don't do any backprop at all. So if you look at this equation, which is the equation for updating the weights, you'll see that there is no error term here. Instead, eta, which is the learning rate, and x and z are just the input vectors and the activation vectors. And t is a threshold that I talk about later, but that again is not dependent on any error or feedback. So our work is motivated by the fact that current algorithms, and there's only very few which do Hebbian learning, are slow and complex. So for instance, state-of-the-art network from Krotov uses two-phase training regime, which means that both their layers cannot be trained parallelly, but they have to train the first layer first for about 1,000 epochs, then they freeze that layer, and then they train the SGD weights separately, which is the second layer, for another 500 epochs. Also, they require 5 distinct hyperparameters for their algorithm on top of the standard hyperparameters that we are used to. And they also require about 12,000 runs to find the optimal value of these hyperparameters. So we try to reduce this complexity by essentially proposing two new rules on how to do Hebbian learning. So now this is the equation for the vanilla Hebbian learning rule, which is just a multiplication of the two activations. In our case, that's the input vector x and the activation vector z. However, we find that this is not very stable, and the first step to stabilizing it is to threshold this product on something. And we realize that a good way to do that is to threshold it on all the past uh, activation products that a particular neuron has, a particular weight has seen. So for instance, if I'm at the tth training iteration, then I will threshold my tth weight update value on all the previous t minus 1 products that that particular weight has seen. Secondly, we also introduce sparsity in the weight updates. We don't update all the weights, but we only update a percentage of them because we again realize that doing a lot of updates on the weights in each batch actually overrides the pattern information that is learned by the neurons. And so to preserve patterns and to improve the representation power, we actually need to only sparsely update the weights. And so we set a very simple rule for that. We only update the top 1% of the weights and we don't update the others. So it's again a very simple rule to apply. And both of these help us reduce complexity quite a lot. So we can now train both the layers in one go in parallel. We also need lesser number of epochs, and we only have one new hyperparameter, which essentially is m, which is the sparsity ratio. So we set that as 1%, and we only required about 13 runs to find that optimal value. So the complexity is much lower. Now, if we look at the ablations that we did for each of these rules to understand them better, so the vanilla rule actually doesn't really learn anything, and these are numbers on MNIST. With thresholding, we actually increase our accuracy to 65%, which is represented by the screen line. However, after an initial increase, this accuracy decreases and it stabilizes at a much lower value. Lastly, when we add the sparsity, we see that the accuracy even increase above 90%, and at the same time it stabilizes very well, and it's now a nice stable learning that we see. So the combination of all these three rules really helps. We also plot what the neurons are actually learning in this graph here. and each of these sub boxes represents a particular neuron. We show a sample of 28 neurons here, and we see that the red color here represents positive weights and blue represents negative weights. So we see the neurons learning many different kinds of patterns. They learn positive patterns where this digit is being learned through positive weights, but also negative patterns. So this digit, again 9, is being learned through negative weights. We also see partial patterns like the small red arc, and we also see two patterns being learned at the same time. So digit 9 represented by the red weights, but also a negative pattern which is represented by the blue weights. So that's really nice because our neurons are not just learning a single pattern like a single digit, but they're actually learning much more nuanced information than that, where they can learn either partial patterns, full patterns, or actually multiple patterns, which improves our representation capacity. Now, finally, if we look at the results, and these are results on CIFAR 10, we see that our algorithm HEBNET beats the backprop by quite a lot, and we test backprop with the same hyperparameters as HEPNET, but also when we specifically tune the hyperparameters for backprop, HEPNET still beats them. It also beats another work by Amato et al., which is another Hebbian learning work. And lastly, compared to the state of the art, we are pretty close, but we reduced the number of epochs by quite a lot, by 7.5 times actually. So if you want to know more or if you have more questions, please visit us at poster number 20. And with that, I've come to the end of my presentation. Hope you have a great day.